Okay, so it's a pleasure to reconvene once again, and this talk will be delivered by Dr. Melissa van Beekveld from Oxford University, and she is going to continue on the topic, the dark side of SUSY. Okay, all right. So we will take the questions at the end, Melissa. Will that be okay?
Yeah, that's fine. I mean, if there are any urgent questions during the talk, I would also happy to answer right away.
Okay, all right, all right. Okay, all right. So you may start.
Okay, thank you so much. So I want to start, of course, this talk by first thanking the organizers for giving me the opportunity to talk about this here. And also, of course, to host this amazing conference. So I heard Rohini told me that actually this conference was to be held before the pandemic started, and then we could have all visited in person. And then really, it's a shame that this doesn't happen now. But hopefully, this online format is a good substitute still. So indeed, I will continue on discussing the dark side of SUSY, as my title says. I mean, Genevieve did a very good job in giving the overview, but I know how hard it is to remember things the first time you see them. So I will just go over some of the concepts that were introduced by Genevieve. First of all, we have a lot of evidence that dark matter should be out there somewhere. So indeed, we have these rotation curves that don't look quite right if we try to compute them with the normal laws of gravity. We need dark matter to form deep enough gravitational wells to enhance or speed up the process of structure formation. We need it to explain the cosmic microwave power spectrum. And we need it to explain observations that we do in gravitational lensing. And one very famous example is this system of colliding clusters, the bullet cluster, where we see that although we expect that the majority of the mass would be residing at the place where these clusters had collided, actually what we see is that the majority of the mass lives on the outskirts of this system. And then there's also a very recent discovery, and there are more and more discoveries being made in that area, where we actually find systems of galaxies that don't have dark matter. So these are galaxies where if you measure their rotation curves, they follow the ordinary curve that you would expect based on the ordinary laws of gravity. And so there are a few of these systems have been found to this date. It is, for some of them, it's, and for example, for this one, I think it's unclear whether actually the analysis was done properly and whether the distance in particular was measured properly. But still, if this is true, if there indeed are galaxies without dark matter, that's actually a good sign for the hypothesis where dark matter is composed of new particles. Because if you do computer simulations of, for example, structure formation, you do predict that such systems need to exist. So finding them is a good thing. So the leading hypothesis to explain all of this information is that there is a new type of particle that does not follow the laws of the standard model. And indeed, there is no candidate in the standard model that can account for this dark matter. So there is a need for new physics. Now, a prime candidate, of course, to introduce this dark matter particle is supersymmetry. Because supersymmetry, depending on exactly how you realize it, offers a variety of electrically neutral, non-baryonic, stable, and non-relativistic dark matter candidates. And we've seen that if you assume that the dark matter particle is a weakly interacting massive particle, then its relic density is given by this simple formula. And indeed, I will not consider other scenarios during my talk. The second reason why we like supersymmetry is that it offers a solution to the fine-tuning problem. And since this is a very delicate problem that will play a major role in this talk, I want to go over it a little bit. So what is the fine-tuning problem? The fine-tuning problem is a problem of the Higgs boson mass, and it's the issue of how the Higgs boson mass depends on other fundamental parameters. So if you go out and measure the Higgs boson mass, all that you do is you try and measure this resonance distribution. The place where this resonance peaks is what we call the Higgs boson mass, and its width is the decay width. Now, how do we relate such a measurement to theory parameters, this MH? So if I try to explain what happens here in theory, then I find a Feynman diagram that looks like this. I produce my Higgs boson. This then decays, in this case, to two Z bosons, which then substantially decay into a pair of leptons. And then if I just go through the ordinary Feynman rules, I find that this propagator is described by this 1/p² minus m². However, I know very well that the Higgs boson lives in a quantum theory, and in a quantum theory, a particle is never alone. It will always be accompanied by other particles, such that the propagator actually receives quantum corrections. And it's this complete sum, so the bare mass plus the self-energy corrections, which are denoted by this I pi, this complete sum is what we measure in experiments and give the label of having the physical Higgs boson mass. Now, what is the usual story about fine-tuning? It is, if I go ahead and calculate these self-energy corrections, I find that these diagrams are actually divergent. So I need something to capture this infinity. And a way of doing that is saying that the standard model is only an effective theory bound to break down at some high enough energy scale. So if I put this energy scale to the Planck scale, the scale where the effects of gravity are certainly to kick in, then I find that these self-energy corrections are of the order of this Planck scale squared. And indeed, if I then need to fine-tune that number, this bare Higgs parameter, such that I get 125 GeV out, surely there must be a large degree of fine-tuning going on. However, this story is completely wrong. It's often told this way, but it's really wrong, because all that you've done is you've introduced a cutoff on your integrals, and you can get rid of this cutoff, this unphysical cutoff, by a process that we call renormalization. We capture the infinity by renormalizing our bare parameters in our Lagrangian. And indeed, you can see the problem in a different way if you just use a different regulator. So instead of using this cutoff regulator, let us use dimensional regularization, where you introduce this parameter epsilon, and in the end you take epsilon to 0 to retrieve your calculation in 4 space-time dimensions. And if you do that, you find that this self-energy correction, the first term is proportional to this divergence, which has the role of this cutoff. And the second term is a logarithm. But note now that this logarithm is multiplied by a term that is the fermionic mass term. So really the mass of the fermion that goes around in this loop. And this is really the issue that underlies fine-tuning. We see here that quantum corrections to the Higgs boson mass, this thing, they are not proportional to the Higgs mass itself, but instead they are proportional to fermionic masses. Now, in the standard model, the heaviest mass that we have is that of the top quark. So that means that this self-energy correction grows of the order of the top quark mass, which means that there is not a lot of fine-tuning needed in the standard model. However, once we expand the standard model and allow for a theory of dark matter or of supersymmetry or whatever, then we may introduce fine-tuning because we're introducing a new mass scale that actually can push up this number quite a lot. Now, why do we worry about fine-tuning? The reason is as follows. We are used to describing our world using effective theories. And to give an example, we do not need a quantum mechanical description of gravity to explain how apples fall from trees. And in a similar way, we don't need knowledge of the Planck scale to understand what happens at the LHC. And this is because nature obeys a very powerful principle. There's a factorization of high-scale physics that decouples from low-scale physics. However, in the Higgs sector, this principle seems to break down because the Higgs boson mass is inherently sensitive to what happens at the highest scale that you have in your theory. And it really feels like this breakdown of this principle in the Higgs sector is trying to tell us something. It's telling us that there's something that we don't understand yet about our theory. Now, the question that I'm going to ask during this talk is whether we can accommodate both dark matter and fine-tuning simultaneously. So let me go back to my title screen and actually change the title of my talk slightly, because what I will discuss is the low fine-tuned dark side, not of SUSY, but of the PMSSM. So going from supersymmetry to the PMSSM, I mean, what you do is you really just do the simplest extension of the standard model that you can imagine. And then you introduce some phenomenological constraints to constrain the number of parameters that you have. And then dark matter candidates that you obtain are two. So first we have this neutrino, and secondly we have the lightest neutralino. So I put this neutrino one between quotes because, as Genevieve also explained, this one is actually excluded by direct detection experiments. And this one is the only candidate that is still alive. Now, the PMSSM also offers a solution to the fine-tuning problem. Supersymmetry in general does that because supersymmetry links scalar mass terms to fermionic mass terms. And fermionic mass terms have this property that the quantum corrections are indeed proportional to the bare mass itself, because they're protected by this chiral symmetry breaking. And as long as you break supersymmetry soft, then this property is also guaranteed for the scalar mass terms. However, by introducing supersymmetry, you also want to, in the end, obtain a spectrum that is consistent with the electroweak symmetry breaking. And by requiring that, you get a bunch of equations that link the Z boson mass to the internal supersymmetry parameters. And by doing so, you actually introduce another fine-tuning problem. So why is that? Well, here you can see that if I take, for example, mu to have a very high number, then there needs to be a cancellation in this sum such that I get a Z boson out of roughly 91 GeV. So indeed, there is a second fine-tuning problem that you introduce here. Now, there are several ways how to quantify the fine-tuning. I will make use of this electroweak fine-tuning. There are arguments for this, but I won't go over that. The electroweak fine-tuning is just given by comparing the size of all of these contributions to the size of the Higgs boson, of the Z boson mass. And to have this electroweak fine-tuning measure less than 100, we need mu to be less than 1 TeV. Now, there's one thing that I want to say about these fine-tuning measures, namely that quantifying how much fine-tuning there is in a theory, this is not something that is subjective. You can do that in a scientifically found way. Where there's room for discussion is how much fine-tuning you allow in a theory. And this is also where a lot of the discussion, I think, around fine-tuning comes from, that this number, I put an upper limit of 100 on fine-tuning, but why not 1,000? Why not 10? This is subject to discussion, and I think that this is why, indeed, there's so much controversy around fine-tuning. But this is what I will assume in this talk. Now, I also want to have dark matter. So how do I get the relic density? So Genevieve went over this. What you do is you derive the number density of the dark matter species using a Boltzmann evolution equation, where the sigma v describes the cross-section of dark matter particles into standard model processes. And it contains also a thermal averaging over the initial state velocities that we had in the early universe. Now, at some point, during the early universe, the universe is also expanding, and at some point, really the mixture gets too dilute for these dark matter particles to find each other. And in that case, we have a freeze out, and this number density approaches a constant that we call the relic density. This relic density can be measured by fitting the lambda CDM model to this cosmic microwave background. The cosmic microwave background is observed by Planck, and Planck tells us that the dark matter relic density is this number. Now, how to obtain the right relic density in supersymmetry? So there are basically three mechanisms that allow you to deplete the dark matter relic density. The first one, which I call the vanilla scenario, is that you just take a large enough annihilation cross-section and a compatible mass. So what do I mean by that? Well, this sigma is proportional to the coupling to the power 4, so the coupling of dark matter to standard model particles, divided by the mass of the dark matter squared. So you just take two compatible numbers here and make sure that in this ratio, you get out this 0.12 as measured by Planck. Then there's a second scenario which is the co-annihilation scenario. And this happens if there is a small mass gap between the dark matter particle and another supersymmetric particle. And in this case, the sigma V contains contributions both from this annihilation process, but also where the dark matter is co-annihilating with another supersymmetric particle. And really, this supersymmetric particle can be anything. And then lastly, we have the funnel regions where we have an S-channel resonance of this decay. For example, this may happen via a Z boson or Higgs boson or a heavy Higgs boson. What these models all have in common is that the mass of the dark matter particle is slightly less than the mass of the resonance boson divided by 2. And the reason that it's slightly less is because also you have this thermal velocity that gives a bit of kinetic energy. And therefore, it pushes the total invariant mass of this annihilation on shell for this S-channel resonance. And that's really because these early universe velocities are quite high. Now, as the universe cools down, also their velocities get lower, which means that the present day annihilation cross-section can actually be orders of magnitude smaller than the early universe one. And we will see explicit examples of this in what follows. So how then to relate this to the PMSSM? Well, first we need to understand what the relevant parameters are. So just to go over them very briefly, we have M1, M2, and mu, which are the bino-higgsino and higgsino mass parameters. And we have tangent beta, which is the ratio of the vacuum expectation values of the two Higgs fields. Whenever the absolute magnitude of M1 is smallest, then we have a dark matter particle that is bino-like. If M2 is smallest, we have a Wino-like dark matter particle, and its mass is degenerate with the lightest chargino, which is denoted by this, and we'll refer to as chi1. Whenever mu is smallest, we have a higgsino-like dark matter particle, and it will be degenerate with chi1 and which I refer to as N2. Now, when do we get a thermal relic which satisfies this constraint? There are 4 types of scenarios that we have. First of all, we can have a pure Wino, which is with a mass of around 2.5 TeV. We can have a pure Higgsino with a mass around 800 GeV. And then we can have a mixed bino-higgsino or bino-Wino with a mass of around 100 GeV. So these all belong to this vanilla type of scenario that I discussed before. The reason that you have Wino with the highest mass is just that the Wino couples most efficiently to standard model particles. So therefore, you need to have a higher mass to get the right relic density. Now, there's also a fourth one where we have an almost pure bino, which doesn't couple very efficiently to standard model particles, but it's found nonetheless in these funnel regions and also due to this co-annihilation mechanism. Now, if we also throw in fine-tuning in the mix, we find that these two solutions are actually not ideal to get low fine-tuned solutions, because this would require mu to be larger than 2.5 TeV, and this one would require mu to be larger than 800 GeV, pushing it very close to this upper limit of 100 that we imposed. So we're going to look at only these 2 scenarios, and we're going to ask the question, which of those scenarios is viable after taking into account the experimental constraints? Now, we've already seen that there are several ways to detect dark matter. So either you read this diagram from left to right, in which case you break dark matter, and this is relevant for indirect detection, but also for the relic density calculation. You can read this diagram from top to bottom, in which case you shake dark matter. Dark matter is bumping into a standard model particle, and this process is relevant for direct detection. And you can read this diagram from right to left. In this case, we make dark matter, for example, at particle colliders. So all of these experiments have constraints on the allowed parameter space. So we have to take them into account. So here I quickly flash the analysis chain that we have. We have something that accounts for the collider process limits. We have something that accounts for the indirect detection limits and the direct detection limits. And then we also throw in these constraints that originate from G-2, so the recent analysis that was published in April, and B-physics observables. So if we do all of that, we scan SUSY parameter space, this is what we get out. So here you can see the present day annihilation cross-section as a function of the dark matter mass. First thing to note is that this is the ballpark of annihilation cross-sections that is predicted for a thermal relic. And you can see that most of the vanilla type channels are therefore not there anymore in the PMSSM parameter space. The majority of the parameter space is taken either by these funnel regions, which are labeled by 1, or by co-annihilation regions, which are these things, which are labeled by 2. So what I will do for you in the remaining time is go over each of these regions, discuss the LHC and discuss the LHC phenomenology. So first of all, the funnel region. So what you can see is that there are two of these structures that stretch down all of the way to very low values of the sigma V. And there's one around dark matter mass of roughly 40 GeV and one around dark matter mass of roughly 90 GeV. So this one is slightly less than the Z mass over 2, and this one is slightly less than the Higgs mass over 2. So these models are characterized by very small bino-higgsino components. The heavier states, Chi1 and N2, these are mass degenerate with each other, and they have masses between 100 and 500 GeV. The collider signature that are relevant to probe these channels are either this N2 decaying into a Higgs or a Z boson plus a lightest neutralino. This decay can happen either on shell or off shell, depending on the mass gap between the lightest neutralino and this N2. And for the Chi2, we have a decay to a W boson and the lightest neutralino. So there are a few searches that are relevant to these scenarios. However, the region where the mass difference between N2 and the lightest neutralino is in between the Z mass and the Higgs boson mass, this region is relatively unconstrained by the experiment, simply because here you need to take into account this off-shell decay of a Higgs boson, and the experiments are not looking at that at the moment. So this is the funnel region. What about those co-annihilation regions? Three of them. Let me start with the slept-on co-annihilation region. We have two of them. So there is one where we take into account the first and second generation slept-ons to have a small mass difference with the lightest neutralino. So what you see in this plot is the slept-on mass as a function of this mass difference. And you can see that the mass difference is between 30 and 10 GeV. So in these models, we have a strongly bino-like lightest neutralino, and we have Higgsino-like heavier states. Only spectra where the mass difference between N2 and the lightest neutralino are smaller than MZ survive. And the reason for that is that the LHC experiments are heavily constraining the region where this is larger than MZ, because they look for decays that look like that go like this.
Hi, can I just have a clarification here? I mean, in this particular plot, you show actually co-annihilation region together with the annihilations to BB bar, TT bar, and other channels like funnel regions also, right?
Yes, indeed.
Okay. Yeah.
Yes, so indeed, only the yellow points.
Yeah.
So
yeah.
what I'm denoting here holds for the yellow points. But indeed, I'm also showing the other colors are given by the other channels. Indeed. Thank you for that.
Thank you.
So then the second one, which is the Stau correlation region, here we find, so it's the same plot as this one, but then we have the Stau mass on the horizontal axis and the difference on the vertical axis. We have a bino-higgsino N1, and we know like heavier states, which is quite surprising, but this can happen just due to the structure of the mixing matrix. We have Stau-mediated decays of these heavier states. However, they have no sensitivity because the mass difference, as you can see, between the Stau and the lightest neutralino is a lot less than 100 GeV. And this makes the search for these kind of decays very challenging because you don't have a lot of missing transverse energy to play with. However, it is important to also probe this region. A dedicated low mass would really be nice to have here. Also, what I want to point out is that this is actually the only region where the dark matter particle can still have a mass between roughly 70 and 100 GeV. All the other scenarios are either excluded by the LHC experiments or by direct detection experiments, but this one is still viable. Okay. So it is an interesting, yeah.
Yeah, I had another short question. So this PMSSM spectrum is actually generated at the low scale itself, and there is no correlation at the high scale.
Precisely, it's an effective model for these scenarios. Yes.
Okay. Yeah.
I mean, you could translate them also in gut theory, but this is also why we use this electroweak fine-tuning measure. We want to be agnostic about what happens at the high scale.
Mm-hmm. Okay. Yeah.
Yes. So the second region is unprobed at the LHC at this moment, and I'm working with a master student to see whether we can actually devise some search strategy for these scenarios, because they really are interesting and it's at this point in the analyses. Then the last region that we have in this co-annihilation scenario is that of where the co-annihilation partner is a chargino or this second lightest neutralino, indicated by these red points. Here we have a bino-like N1 and Higgsino-like Chi1 and N2. And we see we have compressed spectrum where the mass difference is roughly between 15 and 20 GeV. And it cuts off sharply here. And this is because the LHC experiments are actually sensitive to this region. And really what is limiting the sensitivity to that region is statistics. Once we crank up the statistics, I expect that we can probe a larger fraction of that region. The final region that I want to discuss is this region that is labeled by BB bar and TT bar, which is actually the bino-higgsino region. So here we have a big bino-higgsino lightest supersymmetric particle, and it has masses between roughly 140 GeV and 500 GeV. So why do I label them by BB bar and TT bar? Well, that's because the decays of these particles are actually mediated by Z or Higgs exchanges. And so this lightest supersymmetric particle is a Majorana fermion, which means that if it annihilates via Z boson, this annihilation is actually helicity suppressed. So it will always pick the heaviest standard model particle state that it can decay into, which is if you're below the mass of the top quark, the B quark. But as soon as you cross this threshold, then you're heavy enough to produce 2 top quarks on shell, so that decay will be preferred. Now, there are also still models where we have this BB bar scenario, and those are scenarios where the value of tangent beta is very much enhanced, because this cranks up the Yukawa coupling, the bottom Yukawa coupling to Higgs bosons, making that decay preferred.
Okay. Another thing is that I think the time is almost over.
Yeah, I have 2 slides.
Okay. Thank you.
So in this case, Chi1 and N2 are Higgsino-like with masses between 200 and 500 GeV. And the collider has really little sensitivity because, again, we have limited statistics. There's a small production cross-section for these Higgsino-like N2 and Chi1. But if we crank up the statistics, also this region can be probed. So far I've only talked about the LHC experiments, but there are also other experiments that we need to take into account. And one that is really highly relevant here is future dark matter direct experiments. So what I show you here is the spin-dependent cross-section as a function of the dark matter mass. And in color code, we have this fine-tuning measure. And I show you these two projected limits where you see that actually all of these models in the future can be probed by these experiments. So even if they're very difficult to find at the LHC, we will have sensitivity to them. And this brings me to the conclusion. So we see that we find solutions that are minimally fine-tuned, give the right dark matter relic density, and offer an explanation for this G-2 excess. We have these three branches of solutions that I discussed. Of those, the Stau correlation region really misses some sensitivity, would be good to probe it. However, on the other hand, dark matter direct detection experiments will probe the region entirely. Now, if you're interested in looking into these models in a little bit more detail, all of the data that is necessary to produce these plots can be downloaded from this website, and invite you to go ahead and take a look at that. And with that, I want to thank you for your attention.
Thank you very much, Melissa. And now I think it's time that we can take up some more questions.
Mm-hmm.
Laura, yeah, please go ahead, Laura. Yeah.
Okay. Hi. Yeah, thanks for the nice talk. I was teaching, so I only saw part of it, but I just have a question on your last remark here and the last plots, which are very nice. Whether you also have the cross sections on the spin dependent, on the neutrons. So the spin dependent cross section on neutrons. I was wondering.
Yes, I have them, but not in the slides. I'm sorry. But they look very similar. Yes, they look very similar.
Okay, because of course some experiments, as you know, have higher sensitivity to the neutron. Of course, we always make the assumption that the other one is 0 when we set this kind of limits, right? But
yeah. No, I have the other plots, and indeed so some of the points, of course, shift a little bit, but the general story is the same. Also, if you would only be sensitive to the coupling with the neutrons, you get the same.
I see.
Yeah.
Okay. Well, that's good to know. Thanks. Yeah.
Mm-hmm. Thank you for your question.
If there is any other question. If not, can I ask you one more thing? It's rather a clarification, actually. So when you are producing all these Higgsino dominated or bino-higgsino regions or something, so what is the limit on the Higgsino domination or bino-higgsino mixing that you are actually allowing? So that was my question.
I don't impose any limit on the amount of mixing that is allowed. So I let it. So how we do this technically is we use something that's called a particle filter. So we just search for interesting solutions, and we allow anything that pops up. We don't say it needs to be in this constraint in this particular region. So we find indeed solutions that have almost a pure bino, and we find solutions that have a pure Higgsino component, but these pure Higgsino ones, they are very heavy. So they do actually satisfy the requirement that its fine-tuning is less than 100, but they don't offer an explanation for the G-2. So that's why they don't pop up here.
Okay. Yeah, okay. With that, then if no further questions are there, then we can thank Dr. Melissa for a wonderful talk. Thank you so very much.
Thank you too.
Thank you, Melissa.